Tabiri, who will talk about plane curves, which are quantum homogeneous spaces. So take it away, Angela.
Thank you very much, Karen, and to the organizers for inviting me to speak. As Karen said, my talk will be on plane curves, which are quantum homogeneous spaces. And this is joined with my PhD supervisors, Ken Brown and Ulrich Kramer. There are two papers on this, the first and the second, and they are both available on the archive if anyone wants to check. Okay, so just a brief outline of today's talk. I'll start with a bit of motivation. So we are interested in looking at links between algebraic geometry and algebra. So on one side, you have algebraic tools, and on another side, you have algebraic geometry tools, and we want to see some sort of correspondence between them. But there are also some preliminaries. So I know the audience is very broad here, so I'll go through some preliminaries on what an algebra is, what a co-algebra is, what a Hopf algebra is. So my apologies if you already know these. You would have to maybe mute for a while so that it doesn't look too basic to you. Then I'll talk about these two new Hopf algebras that we discovered. So we call them AX-AG and AGF. And what are these inputs? These inputs are just the equations given by a plane curve, and we have a very beautiful theorem which I'll mention. The theorem holds in general for all of these. These Hopf algebras exist in general for certain class of equations, but the theorem has a little bit of restrictions. Okay, so let's start with a little bit of motivation. So as I mentioned, we are trying to look at things between. So on this side of my curve, I have some algebra going here. And on this side here, we have some algebraic geometry. Okay. So what is all this? So there is a classical correspondence between the category of commutative affine Hopf algebras. I'll define this shortly. So affine means that it is finitely generated, and the category of affine algebraic group over a field K. And throughout the talk, K will be an algebraically closed field of characteristic 0. Okay, so what is an algebraic group? So think of the zero set of some ideal of polynomials. But the reason why it's a group is that you want your multiplication and your inverse maps to be continuous here. So how do we get the maps both directions? So if we take the algebra side, you have affine commutative Hopf algebra. So if you take an affine commutative Hopf algebra H, then there's a theorem in commutative algebra that any affine commutative Hopf algebra is isomorphic to the quotient of the polynomials in some variables n by some ideal generated by some polynomials. So given this way of identifying an affine commutative Hopf algebra, we get an algebraic group by looking at the zero set of this. So zero set, look at all points which vanish on this ideal. So that would be an algebraic group. Then similarly, given an algebraic group G, you look at the coordinate ring. So here O of G is the coordinate ring. So you can think of functions on the group. So this is a Hopf algebra, and we will see some examples of Hopf algebra. So this is a very beautiful correspondence where you see some algebra going on here and some geometry going on here. But what are we interested in? We are interested in homogeneous spaces. So in the commutative setting, what is a homogeneous space? So a homogeneous space is a space such that a group acts transitively on it. Okay, so you can think of the two sphere in R3. So homogeneous space means look at every point looks the same. Every point in the space looks the same. So if you look at the sphere, every point on the sphere looks the same because it's sort of curves. The curvature is the same everywhere on the sphere. So when you think of homogeneous space, you think of the two sphere. But here we are looking at it in terms of algebraic geometry. So in terms of geometry, if you have an affine algebraic group G, and a closed subgroup, then you can find the quotient of your group by the subgroup H, and that will be the space of cosets. And in that space of cosets, the group acts transitively on it. Transitively means that for every point in the cosets, you can have another point in your group which takes you from one coset to the other. So in here, we have the homogeneous spaces given by these, but that theory is developed, and we are more interested in non-commutative things. So we want to look at the analog of a homogeneous space in the non-commutative setting. So you ask yourself, you see that in the commutative setting, the homogeneous space was the quotient of an affine algebraic group by a closed subgroup. So you might think that when you move to a non-commutative setting, groups generalize Hopf algebra. So you might think that the non-commutative analog will be you finding the quotient of a Hopf algebra by a Hopf subalgebra. But it turns out that that is more restrictive. Why? Because a Hopf subalgebra seems to be a stronger condition, and we need something a little bit weaker in order to define it. And that weaker thing we need is something we call a right co-ideal subalgebra, which I will define very shortly. But also, we mentioned that homogeneous spaces in the classical setting, it has a group acting transitively on this. So this is more of the geometric side. But when you bring it to the algebra side, the transitive group action translates into something called faithful flatness. Faithful flatness. So it turns out that the right analog of a homogeneous space in the non-commutative setting is a quantum homogeneous space, which we define as some right co-ideal subalgebra of the Hopf algebra such that some faithful flatness property is satisfied. And this is there's an example of this is Pogge's quantum sphere, which cannot be realized as a Hopf subalgebra of the Hopf algebra, but it's a quantum homogeneous space. So that's what we are interested in. So we are interested in non-commutative Hopf algebras which have some nice geometry going on in there. Okay. So just a brief recap. So I'm just going to go through what an algebra, co-algebra is. So please, apologies if you already know this. I apologize for this, but I would like to make sure everyone has an idea of what a Hopf algebra is. So what is an algebra? So an algebra is just a vector space with two maps, the multiplication and the unit map, such that this diagram commutes. So the fact that this diagram commutes means that you have associativity. So here you have associativity. So if you have three things, there are different ways of you multiplying them. Is the fact that this diagram commutes. And the second property is that you want a unit property, which means that you have a right unit and a left unit multiplying in your space. So that's an algebra. And for an example, you think of the group algebra of a group over a field. So just finite linear combinations of group elements. So it will satisfy the associativity and the unit property. But very often in algebra, we like to dualize things. So an algebra, we dualize it by bringing some co in front. So whatever maps we have, we just reverse it. So here we had a map moving from A tensor A to A, but for the co-algebra, you now reflip your arrows. So now you move from A to A tensor A, and you also flip this arrow. So you no longer move from your field to A, but you rather move from A to A. So we call this map the co-product or co-multiplication, and we call this the co-unit. So you just add co to whatever we had before. And the diagrams that commute, we want co-associativity. So we just flip these arrows here, and that gives us the co-associative property. So you can think of the co-product as some sort of splitting map. It picks an element and it splits it into two. And if it splits into two, you can, okay. So this is supposed to be a delta, yes. You can either apply the co-product in the first component here and do nothing here and land here, or after applying your co-product, you can now do your co-product in your first component and do nothing in the second component. So you want this diagram to commute, and for it to commute, that's the co-associativity. commutativity, and you want the co-unit property to also hold here. Okay, so another example, think of the group algebra. So we define the co-product of your group algebra to be G tensor G. So the basis is just the group, so it's enough to define it on this, and it extends linearly to this, and you define the co-unit of it to be just 1. Okay, you can check that all these properties are satisfied. Okay, so we now know what an algebra is. So think of an algebra as some vector space where you can multiply things, and a co-algebra is the dual of it, so some vector space where you can split things. But we want these two structures to interact very well, so that leaves us to a bialgebra. So a bialgebra is also vector space such that you have both the algebra and the co-algebra structures, but you want these two structures to interact very nicely. So you want your algebra and your co-algebra to satisfy some compatibility conditions. And what are these? So in your algebra, you have that there are some multiplication and co-unit, but the algebra also you also have a co-algebra there. So you want that algebra, those maps M and M, to be co-algebra homomorphism. That means you want them not only to respect the algebra structure, but you also want them to respect the co-algebra structure. Which means that if you apply your co-product and you apply M tensor M, you want it to be the same as you first multiplying and applying your co-product. And similarly, you want your unit map to be a co-algebra homomorphism. So you want it to preserve the co-algebra structure given by this condition. And or equivalently, you want your co-algebra maps, which already are co-algebra homomorphisms, you want them to respect the algebra structure. So you also want them to be algebra homomorphisms, which is given by this. And an example is, think of the group algebra. So for the group algebra, both the algebra and the co-algebra structures are compatible. Great. So finally, we get to what we are looking for is a Hoff algebra. So a Hoff algebra is a bialgebra, but with some extra map S. And this S is what we call as the antipode, which is an anti-homomorphism. So it is a structure reversing map. So if you have, let's say, S of A times B, it becomes S of B times S of A. So it is an anti-homomorphism. But what's other compatibility condition do we get from this? So don't forget the bialgebra, these maps interact very nicely. But now you are adding another map S, which is called the antipode. So you want all these 5 maps to interact nicely, and that is summarized in this diagram here. So you want this diagram to commute, and the fact that this diagram commutes means that you have a Hoff algebra. So a Hoff algebra is just some vector space with a multiplication, a co-product, a unit, a co-unit, and an antipode, such that some compatibility conditions are satisfied. So you have the bialgebra, KG, but for it to become a Hoff algebra, we just have to define the antipode as S of G is G inverse. So think of the antipode as a generalization of the inverse map of a group. Another example would be the universal enveloping algebra of the algebra. That's an example of a Hoff algebra. Okay, so all these examples are classical Hoff algebras, and I will explain what do we mean by classical. So they are classical in the sense that if we define a map tau from A tensor A to A tensor A, where it takes A tensor B, so it's called the flip map to B tensor A. Hoff algebra is said to be co-commutative if after you composed the co-product with this, it still gives you your co-product. Okay, so if we come here to that of the group algebra, we see here that if we take our co-product and we flip this, G tensor G flipped is still G tensor G, so it will still give you this. So Hoff algebras which satisfy this property are called co-commutative. And in particular also, Hoff algebras where your underlying group is, group algebras where your underlying group is abelian will be a commutative Hoff algebra. So classical means that your Hoff algebra is either commutative nor co-commutative. So non-classical means neither commutative nor co-commutative. So that's what we are interested in. That's where more interesting things happen. So the first example here is you take the free algebra on these generators, you model out by some ideal of relations. And what are these relations? So here we are interested in some geometry and algebra. So we are going to deal with coordinate rings of plane curves. And the coordinate ring of a plane curve is a commutative affine Hopf algebra. So we always want our x and our y to commute. But these other properties here, we will see comes from the fact that we want your co-products to respect this relation, and that will force these conditions to hold. And this other condition comes from the fact that we are interested in coordinate rings of curves. So this curve you see later on is called the cusp. And the fact that you want your co-products, in order for you to have Hopf algebra, your co-product should respect this relation here, and that forces this relation to happen. And this other relation too is forced by the co-product respecting this. So you have nice relations between your xy, your ab, your ay, your bx, but then the bad relations are between b and y. So you see that b and y here anti-commute, and a and x commute up to a third primitive root of unity. And this is a Hopf algebra with the co-products and antipodes defined this way. So for us, this was a starting point of the research. But so far, we've not defined what a Hopf algebra is. So let's define what it is. And not a Hopf algebra, a quantum homogeneous space. So a right co-ideal subalgebra of a Hopf algebra is first.
I'm Angela. Can I ask a quick question? Where did this come from? Where did you get the Hopf algebra from? The one that you just had?
Also, it was defined in a paper by Ulrich Kramer. So it's an example of a non-commutative, non-co-commutative Hopf algebra.
And do you know where Uli found it?
Come again?
Where did Uli find, or how did he come up with the definition? Do you know?
Yeah, so it comes from the fact that we are looking at coordinate ring. We want a Hopf algebra H, which contains the coordinate ring of a curve. So in this case, of this curve. So if you want this to be a Hopf algebra, you want the ideal of this to be a Hopf ideal. That means you want your co-product to descend to this. So you want your co-product to satisfy this property, co-product of y squared to be equal to the co-product of x cubed. Sure. And you having this will force these relations that we have here. All these relations come from the fact that you want your Hopf algebra to respect this relation. So that's where it comes from. I don't know if it answers you.
Yeah, maybe.
Yeah. Okay. Thank you.
Angela, can I say something?
Yes,
Rita
please.
Fioresi. Yeah, I think I may understand Ramon's question, because it was my question too. I think that he wants to know what is the group structure on a cubic. Are you taking the usual, like all the geometry type of a product on a cubic? You know, there is this strange product where you draw lines and so on. Is this the product that you're taking?
No. So this is just the free algebra. So we are just looking at all words in this. So that it will be an algebra in itself, but the core algebra part is what forces the relation. So we are not really even doing some geometry. For us, we are using algebra techniques to derive all these. So there's no strange geometry going on.
But there is a group structure underlying, isn't it? I mean,
yes, but this is a singular. So there's some singularity going on here. So
I see. Okay.
This is a singular curve. I'll sketch
okay.
it very briefly. So it is not even an affine algebraic group. So
okay, thank you. That totally answers. Thank you very much.
Okay, thank you. Okay, so I'm continuing with a right co-ideal subalgebra. So if you have a subalgebra of a Hopf algebra, if you take the image of your subalgebra under the co-products, you want it to be containing B tensor H. So that would be a right co-ideal subalgebra of a Hopf algebra. So finally, we define a faithfully flat module. So if you have a module over a ring, we say that module is faithfully flat as a left-out module if and only if your functor M tensor R is faithful and exact. That means if you have any sequence of M modules and you apply your functor, you want it to be exact if and only if this is exact. So faithfully flat modules, just think of three modules. So modules which have a basis. So modules with basis. Okay. So finally, we can define a quantum homogeneous space. So a quantum homogeneous space is a right co-ideal subalgebra of the Hopf algebra such that H is faithfully flat as a left and right B module. Okay. So maybe here I might kind of explain your question a little further. So our first question was, which affine commutative Hopf algebras are realized as quantum homogeneous spaces?
Angela, I'm going to interrupt you again. So there's no assumption here that it's Hopf-Galois.
So that's an extra question you can ask, but we didn't answer it in our paper. Some other authors tried to answer. We didn't.
But you didn't need it in the end.
No, we didn't.
Okay, thank you.
Can I say something? I'm sorry, Ramon, to disturb, but I've been thinking about these things a lot. I think that the Hopf-Galois, it's difficult to have in the algebraic setting, isn't it, Angela? I mean,
yes, there's more restrictions. Yeah.
Somehow the faithful flatness is because the Zariski topology is I don't want to say the word bad, but it has very big open. And so for this reason, I think that Hopf-Galois is too much. Am I right, Angela, in saying this?
So it's something I'm not really an expert in. So one of my supervisor students looked at this question, but my knowledge on it is quite limited, so I can't really say much on it.
Yeah, so Ramon, that's the point, that you cannot expect that it's too much for so for very nice spaces like the algebraic groups, you know, the ABCD type, and you take a quotient, they have it, but generic they don't, and so that's why you do faithful flatness.
And this is somehow as well to the fact that these things are not smooth, you know, that they're...
Smoothness, I don't know. Angela,
yes. So smoothness comes from smoothness comes in when you look at affine algebraic groups. So algebraic groups are smooth as varieties. So for the commutative setting, you have the smoothness. So your smoothness comes when you look at affine algebraic groups. But here we are looking at, in general, algebraic varieties. So we are looking at algebraic varieties. So you can have singularities, which we'll see here from the cusp here. So the cusp has a singularity at the origin. So there's no group, it's not a group, it is just a variety. So we are looking in general. Okay. So we were looking at commutative algebras, which are realized as quantum homogeneous spaces. So we are interested in coordinate rings of curves, which are non-commutative analogs of a homogeneous space. So because of the non-commutativity, then we take out groups. So affine algebraic groups are not here. We just look at curves which might have some singularity. So we saw that the cusp was a Hopf algebra in the previous slides, but it is a quantum homogeneous space. So what else do we need? So let's quickly go back to, we need it to be a right co-ideal subalgebra. So right co-ideal subalgebra meant that the image of this should be contained in B tensor H. Okay, now let's look at the way we define our coproduct here. Now, if you look at all the first components of your coproduct of X, they all will be contained in this subalgebra, which is the coordinate ring of your curve, the coproduct of your Y. They all are generated by X and Y. So that means that the cusp here is a right co-ideal subalgebra, but the faithful flatness, we in our paper very often use the fact that it means you have a basis. So you have a basis of your Hopf algebra over this. So this is B. So you get your basis by looking at all powers of this form. So it's like you can pull, it's a basis over B. H is faithfully flat over B. So you can push all your X and your Y's to your left, and the rest will be here. And you can do this using Bergman's diamond lemma. So Bergman's diamond lemma says that if you want to find a basis and you have an algebra, you have to make sure that all ambiguities are resolved. And we will see a little bit more in the next slide. So this was the example Uli worked with when I started my PhD, and he wanted to find more examples because quantum homogeneous spaces is sometimes it's hard to find, there are not enough examples of these. So we started with the nodal cubic, which is kind of similar to the cusp. So it's like you add a non-homogeneous term x squared to it. So we tried using the Hopf algebra he defined initially, but it didn't work. So our relations were all the same with Uli's, except that these two relations were different. So these two relations here are different from what Uli had in the case of the cusp. Don't forget that in the cusp, these relations were that A and X commute up to a third root of unity. So if you had a third root of unity here, all this would have vanished to 0, but these two terms will never be 0. Similarly, if you had a primitive third root of unity so that A and X commute up to a third root of unity, all these homogeneous terms of degree 3 will vanish, but you still have a degree 2 term here. So this seems to be more general than what Uli did. So this was our first paper, where the Hopf algebra structure is the same as the previous one, but the only thing which is different here is these two relations here. And we checked that this was actually a quantum homogeneous space by finding a basis for this. Is there a question? Okay, I thought someone was speaking. So the difference between this basis and the other basis was that the other basis just contained powers of X, powers of Y, powers of B and A, and powers of T. But you see here, we have an extra term AX. So if we call something the GK dimension. So if you look at the growth of your algebra, this Hopf algebra has an extra term here. It has more in dimensions compared to this. So you can say that this has GK dimension 2, but this one has GK dimension 3. So it is a much bigger algebra. So we did this example, but we wanted to generalize this to some class of plane curves. What are these classes? So maybe I'll quickly draw here. So we also looked at the lemniscate. The lemniscate y squared equal to x squared minus x to the power 4. And we realized that the same machinery works, the same relation, but of course we had to modify this other relation here. It worked. Then we also tried the coordinate crossing. So the coordinate crossing is just the x and y axis, which is xy equal to 0. So this didn't quite work until we transformed this into y squared equal to x squared. So it's just rotating it, and it works. And if you look very closely at these three equations, so the first equation is y squared equal to x squared plus x cubed, but that of the cusp on the previous page was this. So if you look very closely here, you see a function of y on one side here, and a function strictly of x on the other side here. So this is strictly a function of x, and this is strictly a function of y, which means that theory worked for plane curves, which can be written as a function of y equal to a function of x. So that's our next definition. So we checked online for literature, and it seems they are called decomposable plane curves. So a curve is said to be decomposable if you can write it as a function of y equal to a function of x. So that means you can't, you don't have any xy, x squared, y squared, you don't have any mixed term there. So the question was that, are these curves general, that, for instance, can you transform any plane curve into a decomposable plane curve? And the answer is no, you can't do so. So there are some special class of plane curves where you can write as a function of x equal to a function of y. And our theory works for such curves, and we show that they are quantum homogeneous spaces. So let's see the setup. So our main theorem is this, that decomposable plane curves of degree at most 5 are quantum homogeneous spaces. So we have 5 here. It was a shame a bit. So initially we wanted, so we have a conjecture that this holds in general, but our proof is only up to degree 5 because we use Bergman's diamond lemma, and I'll mention it, I'll speak a little bit about it briefly. And there you have to resolve ambiguities. And when we were trying it, it was about 30 pages of computations, and it wasn't very elegant. So we just paused there and wanted to see if we could find some more general ways. So in the end, I'll talk about some open problems from our research. So our main theorem is proved using this new Hof algebras that we discovered. So let G be some polynomial in X of degree at most 2. And take note, we don't want constant terms there. If you have a constant term there, you can translate it into one which doesn't have a constant term. So you can translate it to the origin. So we want our polynomial to start from at least degree 1 up to degree n. Then we define the free product of the polynomials in variable x with the log1 polynomial in A. So if you saw from the previous page, the bad relations were between the A and the X, because the rest of the relations was between the A and the X and the B and the Y. So we've separated them to deal with them, then we bring them together, because the rest of the relations were they all commute. So we define a filtration on the subalgebra of F generated by X and A. How we give A degree 1, 0, and X degree 0, 1. Why do we do this? Let me briefly go back to the slide with the relations. So if you look here, you realize that in this relation, apart from, let's forget about this, all the terms here have 2 A's, 2 A's, 2 A's. And if you look here, even the whole relation, all the terms here have 1A, 1A. So the A here is constant throughout the relations, but it is the X that varies. And you see, these kind of mimic your original polynomial, because this will be kind of like the degree 3 parts, and this is the degree 2 parts. This is the degree 3 parts and the degree 2 parts. So this is how we try to resolve it, by defining some polynomial, which is kind of mimicking this using these degrees. Okay, so we give these degrees, then we define some polynomial Pji to be the sum of monomials of degree Ji in this subalgebra. So the sum of monomials in degree Ji. I'll quickly talk about an example which you demonstrate. Where's your J running from? So your J is kind of counting, your J is counting the number of A's. You saw that in all the relations, there was always an A. So your J is moving from 1 to the degree of your, so your n is the degree of your polynomial G, n minus 1, but your I is moving from 0 to n minus 1. Then we define AX, AG to be the quotient of your free product F with the ideal generated by these relations. Okay, so what are these relations here? So on the left-hand side here, on your original polynomial would have been, let's say, x to the power I, right? So what we are doing here is that we are mimicking your x to the power I now with the PJIs. Okay. And we claim that, and the number of relations you get here will be from 1 to the degree of your G minus 1. And we claim that this is a Hof algebra, which we check. So the co-product is the same as the previous one, and the co-units and the antipode. So let's see an example. It might look strange when you look at this here. So an example will be, we said we want our polynomials to be of at least degree 2. So now if your n is degree 2, then your G is just R1 x plus R2 x squared. Then the relation star. So in that case, our star, so let's not forget, star is between the j is between 1 and n minus 1. So when your n is 2, that means you have only one relation, which is this. So our j is 1 and our n is 2. So we have Ri p of j here now is 1, then I minus 1 equal to R1 A squared. So when our I is 1, this becomes 0, so P1 0. When our I is 2, this becomes P1 1 and equal to that. But by definition, what is P1 1? P1 1 is the sum of all monomials of degree 1 0, and that's exactly only A. And P1 2 is the sum of all monomials of degree 1 1, and that is AX and XA. Okay, but we can transform this into this relation here. So we can identify this with a quantum plane at Q equal to -1. So like our Hopf algebras, they can be identified with Hopf algebras which have already been studied, and which was very nice. So for degree 2, it can be identified with a quantum plane, and for degree 3, we will see very shortly, it can be identified with some so-called Down algebras, which I will define. So when n is 3, this is how your polynomial of degree 3 looks like. But then you said your j was between, so your j 1 less than or equal to j less than or equal to 3 minus 1. So your j is 1 and 2. So when j is 1, your relation becomes the sum from I equal to 1 to 3, Ri P1 I minus 1, then R1 A squared. So we have P1 0, P1 1, P1 2. What is P1 0? It is A. What is P1 1? It is AX plus XA. And what is P1 2? It is AX squared plus X squared A plus XA. So these are all monomials of degree 1, 2. Now, when j equals 2, so that means you are summing from 2 to 3, Pj, so it becomes P2, then I minus j equal to this. So it becomes, so this I skip, so this is P2 0, and this is P2 1. Okay, and this is related to some algebra which is called the Down algebra, which I will define very briefly. So okay, so let me just put some aside here. So it's called the Down algebra. So it is an algebra with two generators G and U, such that, so if you have alpha, beta, gamma being complex numbers, it is the algebra with relations d squared u equal to alpha du d plus beta u d squared plus gamma d. So that's one relation. And the other relation is du squared equal to alpha u du plus beta u squared d plus gamma u. So it's almost similar to our Hopf algebra, right? Because you see here, you see this, like these three are like the P2. If we identify D with A and U with X, this is like P21, and these here are like P12. So we get very nice properties for n equal to 3 when we identify our Hopf algebra with what the Down algebra is. But in general, our Hopf algebra has some nice properties. It is pointed. What does it mean? It means that every simple subcoalgebra is one-dimensional. And in particular, if your G is just the monomial x to the power n, then our Hopf algebra has a quotient, which is the localized quantum plane. So the localized quantum plane is a quotient Hopf subalgebra. So it is a Hopf subalgebra which is contained here. But also, if your degree, the degree of your, okay, so it has basis. So if degree, So if the degree of your polynomial, if degree of your polynomial is less than or equal to 5. So this is where we had the challenge. So we were able to prove this up to degree 5. You have a basis. So you can write any element in it as some linear combinations of powers of x, some u, which I'll tell you shortly, and a. What is the u? So u belongs to the free algebra on these relations. So you want to look at all possible powers, a to the power r, x to the power s, such that r and s belong to the set 1 up to n minus 2, and r plus s is less than n. So let's look at an example. When n equal to 3, then that means r and s can only belong to the set 1. Okay, so then in that case, LA is just k of ax. Okay, and that was what we saw in the example of the nodal cubic. So in the nodal cubic, you could see that there was a power of our ax here, and that is coming from this. But in general, if your n, so for n greater than 4, you will always have a free subalgebra. So that means that your algebra is very big. You have a free subalgebra. So you can think of it as your global dimension. If you look at all projective resolutions of this, then the supremum of it will be infinity. So it wasn't quite nice because we wanted some finiteness. If it's finite, then things become nice. So we only get finite nice properties when the degree is 2 or 3, but it's still okay. So if your degree is 3, we have that our half algebra is isomorphic to the down up algebra A minus 1 minus 1, 0. So the down up algebra we defined was A alpha. So the one we defined was A alpha, beta, gamma. So now if your alpha is minus 1, your beta is minus 1, and your gamma is 0. So here, if alpha is minus 1, beta is minus 1, and gamma is 0. So this term goes off. So minus 1, 0. Then our half algebra is isomorphic to this down up algebra. And that helps us to find that it is Noetherian. That means every ideal of it is finitely generated. But it also has GK dimension 3. So what is GK dimension? So GK dimension is just measuring the growth of the algebra, So maybe think of this. If you take the polynomial ring in n variables, k1 up to n, then it has GK dimension n. So it grows like n in powers of n. So if something grows finitely, then it's usually nice. And we realize that if your degree is 3, it goes very nicely. And a global dimension is just the supremum of the length of the projective resolutions of this. Okay, this algebra. Okay, so those are nice properties of AXAG, but we wanted, in order to prove our theory, we want this bigger half algebra. So what are the inputs? You take a decomposable plane curve, f of y equal to g of x. You do AXAG using the right-hand side of your equation, but you also do a similar one. So now instead of having xa, you do a similar one with y. Instead of having b, you just replace your a with b, and instead of having g, you replace your g with f. And f is just a polynomial, and y with degree m. Then we claim that if we define AGF to be the tensor product of these two, modeled by, we need this relation, right? Because we want the coordinate ring of your curve to be a right coideal subalgebra. You want your half algebra to be faithfully flat over it. So you need this. But the fact that you need this and the fact that you want the coproduct to respect this forces this other property. So you see, we've kind of dealt with the bad relations here. And in our big half algebra, we have only two kind of nice relations here. Okay. So this is a half algebra where A is group like, X is 1A skewed primitive, Y is 1B skewed primitive. There's the co-unit and your antipode. Okay. In particular, if we take the coordinate ring of a decomposable plane curve, then this Hopf algebra is free as a left and right B module. So which means that B is a quantum homogeneous space. And I put an asterisk there because currently we have a proof up to degree 5. So I mentioned that I'll briefly talk about the Bergman's diamond lemma. So Bergman's diamond lemma gives you a way of finding bases. And it says that if you have an algebra, you want to check whether you have a basis, you have to check whether ambiguities are resolvable. So resolvable. So I'll just explain an example. So if we consider the AXAG, where the degree of G is 3. We saw that in the relations we had a squared x equal to some plenty things and ax squared was equal to this. But in the algebra, we have the word a squared x squared. This belongs to AXAG. And you see that there are two ways of arriving at this. You can arrive at this by pre-multiplying ax squared by a, or you can arrive at it at post-multiplying ax squared by x, okay? And you want things to be nice, so they'll be nice if all of these are equal, okay? So it's like, so that you can say that there's no ambiguity. Whenever you see this word here, whether you used this to arrive at it or you use this to, oh, sorry, wait, ax squared, oh, I made a mistake here, let me correct it. So this is supposed to be a squared xx here. Okay, so you want to resolve this. So in our paper, we tried to resolve ambiguities up to degree 5 and it was getting too much. So our question, which I will show at the end, is that we want to find another way of doing this. But finally, let's look at some properties of our Agf. They are pointed with group likes generated by some abelian group. So as you saw, your A and your B commute and they are related by this power. But also your Hopf algebra Agf has nice properties when your degree is less than or equal to 3. For example, it is a finite module over its center. It grows like an algebra in this number of variables. So it grows very nicely finitely, and it's also Noetherian. So it's kind of finite. But when you have a singular point at the origin, then of course the global dimension of it, so it explodes. It's no longer smooth, so it explodes. Okay. So finally, I would like to talk about some open questions from our paper. So if you realize, we looked at this construction for decomposable plane curves. So that means curves of the form f of y equal to g of x. But the first question is this: can we do this, not necessarily for this, but in general, so that given any plane curve, I can, so here, our Hopf algebra that we define, you can define it in general for any degree polynomial, but if you want the faithful flatness, then you restrict it to degree n. So we are saying that can we also devise a machinery which gives us some Hopf algebra? So in our case, we had Agf. So you can have some Hopf algebra H such that you have your faithful flatness property holding. We don't know, it's still open. But also the faithful flatness property, so very often people like you to prove it using the functorial way that that functor n tensor over R preserves and reflects exactness, but we proved it using Bergman's diamond lemma. And if you check our paper, you realize that it's a very long proof because you have to go through a long process to resolve ambiguity. So our question is that, can we prove the faithful flatness property in general in a more concise or elegant way without using Bergman's diamond lemma? It is still open. And finally, what are the isomorphism classes of Hopf algebras, Ax, Ag, Agf? When can we say two such Hopf algebras are isomorphic? Does it mean that, let's say if you have degree G equal to 3, is there only one isomorphism class? And when do we even see whether two things are in the same isomorphism class? Some authors have done that for Down algebras, and we would like to see a similar one for these. And we also don't know the isomorphism classes for these. Yeah, I think roughly my 50 minutes is up, and I wouldn't want to go any further. And in my local language, we say medasi to mean thank you. So thank you very much for your audience.
Yeah, okay, so thank you very much for a very nice talk. So are there questions from the audience so far? So are there any more?
Ramon?
Yeah.
I don't know how to raise my hand.
I think you've just done it, no?
So
please ask a question.
can I ask it? So I found this talk very, very interesting. Thank you so much. Now, I have two questions. The first question is that can you have an ordinary group action and an ordinary picture? Because you seem to have your deformation parameters set to roots of 1. But what if you set it to 1? Which groups do you see? I mean, this is, I think, is the same question as Ramon, I think.
So you are referring to the case where
But what is that group action?
Okay, so you were referring to the cusp here. So here, right?
Yes.
So far for all our Hopf algebras, we classify them into two. When you have an nth root of unity, when you have G, if you have your G to the x raised to the power n, then our Hopf algebra doesn't even have a primitive root of unity. It contains such one. So our Hopf algebra is even bigger. It doesn't even need that action. Is broader than this. It doesn't need that group acting on it. So it's a bit strange that we don't use the action of a third root of unity for what we did. I don't know if it answers.
Okay, so you're not seeing B as somehow the fixed points of a coaction. I mean, you are somehow, right?
So we are not. I don't know if I understand your question. Maybe you can come again.
Okay, so you do not. So B is a co-ideal, right?
Yes.
So you can view it as the co-invariant somehow.
Yes, exactly. Yes.
Right.
Yeah.
Is there a way that R you can treat it as a parameter and you set it equal to 1? Can you do that?
I would say no at a glance, because we need some non-commutativity here. Otherwise, yes. You see, because of the singularity here, if you make this 1, then it means everything commutes. And even this, if you make this 1, so it means everything commutes, and it wouldn't operate very nice with the singularity. So you need the non-commutativity.
I see. So when you have the R that I mean, if it's not a primitive root of 1, in that case third, you get a problem. You don't get a nice action. That's what you're saying. Coaction.
Yes.
I see.
Yeah, it's in line with the degree of this side. So if the degree of your this is n, then your R should be an nth primitive.
No, it's clear. No, thank you. It's very clear. Thank you very much.
Okay, so are there other questions? If not, then I have some more questions. I wonder, Angela, is there a Nichols algebra somewhere in the background? Because it,
Yeah, so okay, so we didn't use a Nichols algebra for our work, but they were future directions. So I remember Uli was discussing with it's Van Heckenberger, and he was saying that if we could find the Nichols algebra, he can tell us what class it falls in the classification. So we didn't even compute the Nichols algebra. Those are still open. Yeah.
but it seems like there should be.
Sure, there should be. So these are all directions that we are hoping to explore. So hopefully, if I get graduate students, we can explore some of these directions.
Then I mean, another question is like, are these things quasi triangular?
It's still open. So one of Uli's students, Mariam, she's working more in the line of Hofgallois and some of these other questions. Her results are not yet out, so I can't really tell whether she's been able to check whether these are quasi triangular. But as far as I know, they are all open. We don't know what the out structure is.
So the last one would be like to classify well, I guess in this case, they look more like they're quasi-triangular. To classify the representations of these algebras, again, yeah, I guess this is open.
Yes. So it's one direction I've been thinking of, looking at the representations of these Hof algebras. I think it would be a very nice next step.
Yeah, because I mean, they start to look, I mean, at least to me, they look like the universal developing algebra, the Lie algebra. Because you have this torus, and they look, you have the positive and the negative part. But I mean, again, this goes back to the Nichols question. So
yeah. So maybe once we answer these things, will become clearer. Yeah.
Okay. Thank you.
Okay. Thank you very much.
So, do we have any other questions from anybody?
I have a very quick question. Sorry about this, it'll be fast. So it seems to me that you could try to do some projective, because you could take the projective completion of your cusps, but then you will not be able to get away so easy, right? In that co-invariance, you will need some further concept. Have you tried to explore that direction?
No, so the truth is that I spent 3 years doing this, and at a point I got fed up with it, so I put it away for a while, and I was doing other things. So I'm now gradually coming back to it. So there are lots of open questions which we are yet to explore. So I'll take this further and see if we can answer them. Yeah.
Okay, thank you.
Okay, so I think maybe that's the end of the questions.
Okay.
Yeah, thank Angela again for a very nice talk.